Okay, so in this session we'll be talking about brute force in particular. Now, when we talk about brute force, we are basically saying that given a problem, we want to find some solution or all solutions, and the way we do it is by enumerating on all solutions. Okay, so we try to make whatever moves is possible and try to generate all the possible sets of solution, and out of that, let's say we want to check which of them satisfy this particular condition, or how many of that satisfy some condition that you have rechecked on. So if you're enumerating on everything, that's a technique of brute force. Now, brute force can be implemented either iteratively, right? You can iteratively write a brute force. So let's say this very simple problem that in an array, find out the number of pairs which have, let's say, sum equal to x. So if you write two nested loops to like go on to all two pairs of elements and add their value and check if it is equal to x, okay? If you write something like that, that's a brute force solution, right? Like it's an n square solution, and you are enumerating on all possible choices, and out of that, whichever satisfies the condition, you make a counter variable and increase the counter to counter plus plus. So that's an iterative style of brute force problem. Now, iterative style of implementing it. Now there can be another style which is recursive. So the like most vanilla flavored recursive solution that we generally see is like n queen problem, where you have a board, and let's say we have to place n number of queens, and the way we do it is like keep a track of where all we have placed the queens in the previous rows, and based on that we decide on which row where to place in this particular row. Okay, so there are mostly two types of styles. There are even more ideas that we'll be talking in further sessions, like in the next session particularly, but today we'll be talking about these two styles, and most of today's session would be like solving problems and maybe implementing some of them, because brute force questions can be lengthy implementation, but if you are like good with writing short codes, it helps in writing brute force very fast. Okay, so that's why we would be implementing some of the problems. So that would really the things that we'll be doing today. Okay, so let's first of all talk about something that we can solve using iteration. Just a second. Now, let's say let's start with the first problem then. Let's say you're given an equation a b c d e divided by f g h I j, okay, and it is equal to some value n. Okay, so this is the equation that is given to you. Now you are also given that n follows this equation, that n lies between, let's say, 0 to, okay, it can't be 0, so let's make it 1. N lies from 1 to 70, and n is an integer, and this is not float division, it is a integer division. Okay, sorry, this is not a float division, this is a floating point division. So in case like they don't divide, it will give you a floating number if it's not divisible exactly, right? So that really like gets to the condition that, okay, we need to choose something that such that this divides this, right? Okay, so now the question is, we need to assign a to some digit, let's say 0 or 1 or 2, b to some digit. Okay, so basically we have this a b c d e up to j, and we have to assign them to some corresponding digits, right? Something like this. Okay, so once you assign them, place the digit values in this equation. So this is a 5-digit number that we're talking about. In case a is 0, then it's 4-digit, of course. So we just place the corresponding values, okay, and we check that whether this equation is satisfied or not. Okay, so find out how many assignments of like a to j. So all of these should be distinct. Like it's like you can assign one digit to only one character. Okay, so how many different assignments of 0 to 9 to the characters a to z would satisfy this particular equation, where n is some integer which is not given an input, but it satisfies this particular condition, okay, that it's from 1 to 70. Okay, is the question clear to everyone? So we need to find out the total number of assignments possible which satisfies this form. Okay. So any ideas how do we like brute force the solution? How can it be possible? So it can be some. So we have, so it's not product, it's a 5-digit number. These are digits of the number. Okay, so when I say like I assign, if this is the thing, then the numerator is this number 23109, and the other one is like the other number. So it's like digits. These are digits. This is not product of A, B, C, D. Okay, they are like 5-digit numbers, and upon division they give n. Okay? So we need to find out the number of possible assignments to this. Nested for loops. Okay, so what do you loop on? So there is this condition that each character should get assigned to only one of them, right? Like that's a condition that you need to follow. So how do you write the follow? So let's talk about 3 things over here. There is a n that is there. There is a number A, B, C, D, E, right? There is a number F, G, H, I, J, or there are these characters. Like there are multiple ways to actually loop to solve this particular problem, but we'd be trying to look into what can be more optimal. Right? So how do we loop? If you're suggesting loop, we can loop. There can be other ways as well. Any ideas on this? Recursive. So recursive, you're saying that assign the values and that at the end check which is it satisfying or not, something like that, Shashi? Yeah. So that's one of the solutions. Let's delve into that. So one way would be to, like, we have this particular problem that we have A, B, C, D up to J, and we have to assign 0, 1, 2, 3, 4 to one of these characters, right? So we can do it by recursion, or in fact, there is a very easy way to code this. You can just take this array and, yeah, exactly, and take all of its permutation. And in C++, we know that there is a syntax called next permutation, right? So just take in an array 0 to 9 and call all of its permutation. For every permutation, take the first 5 digit as the first number and the next 5 digit as the next number, and check if it satisfies. Is this clear to everyone or not? Like out of these digits, you can of course construct the number, right? So out of all possible like assignments to these variables, just create the number and check whether it's satisfying the equation or not. Is the idea clear to everyone? Can I have a +1 on the chat, because this is like the most common idea. Okay, and this next permutation will make the code quite easy. So generally we write something like this: do then while we have some, there is while there is next permutation. I'm not writing the full, all of, I mean to say begin command. So if you are writing it in a vector, v dot begin, v dot end. Okay. Should we begin? But I'm not writing all. So this is how you generally write this kind of codes, and inside this you can use the v to create 2 numbers, let's say numerator and denominator, and you can just check if it satisfies it. This is fairly simple. Like I think this you should be able to code by now. Okay. Now, what is the complexity of this particular solution? N factorial. In fact, 10 factorial, right? Okay, it's 10 factorial. It's not order 1. So 10 factorial. It depends upon the number of characters. So over here, it's 10 factorial, and 10 factorial is a pretty large number, right? Like if you think about it, 10 factorial. Passing the limits with 10 factorial is pretty difficult. Like it would be around 5 to 10 to the power 7 or 8. So it's a very large number. Okay. So this particular approach would be inefficient in this particular problem. We can do even better than this. So how do we do better than this? So this is of course one of the ways to solve this, but again, this is getting us a TL. So now how do we improve on this? So okay, now can we split it into powers of 10 and then rearrange the equation? That's possible. That's one way, Tejas. That's a good approach. Vijay is suggesting that NR numerator is less than equal to 98765 and denominator is greater than equal to 0, 1, 2, 3, 4. That's a good observation. So these all ideas that, yeah, exactly. So what we have over here is there are a lot of different things that you can do over here. The main thing is you need to prune the space a bit, right? That there is this equation. So you, first of all, there are a lot of properties that we're not using, that it should be divisible first of all, and then this answer would be between 1 to 70 only, right? This answer should be between 1 to 70. So these are some properties that we're not using while generating all the solutions, right? So now we look into some idea that is called pruning. Okay, the pruning the search. Okay, so there is a search that is going on, but we don't want to go into the like sub solutions which are not even going to give us anything, right? So we will prune those solutions. Like this is not possible, so we don't want to go there. Okay? So of course, for pruning, you can do two things. First of all, change the way you are solving the problem, and the second thing is like look into the constraints a bit and see that okay, this can never happen. Like Vishesh has suggested that okay, numerator can only be up to 98765 and denominator can be from like 1 2 3 4 5, right? Okay. So there are two numbers, right? What if we try to brute force on one and n, like any one of them, let's say try to brute force on one and another and n. Okay, so n has only 70 different values possible, and one of them can only have 10 to the power 5 different values, right? There is a 5, that's a 5-digit number, right? The total number of enumeration that you will have to do is only this much, right? So if you think about this, n can loop from 1 to 70, and then fghij can take from, let's say, 1 to 10. It's not even 1, it's from 1 2 3 4 0 1 2 3 4 to 98765, let's say. Okay, so in that range only it will lie, and then we can just quickly multiply and see, get the value of abcde from the equation, because it has to satisfy the equation. Okay, and then we can check whether the property that all characters got a distinct value is satisfied or not. Make sense what we are trying to do over here? Okay. So what we'd be doing is something like, so what we'll be doing is we would be first of all like trying all possible n's. Okay, so for n equal to 1 to n is less than equal to 70. Okay, so this is like trying all n's, that's it, right? Now we know the value of n that for which we are solving the equation. Then we will solve the value for fghij. Okay, so I'm not writing data types right now. fghij, this is the denominator, right? So fghij can start from 1 2 3 4 only, right? Because all characters has to be distinct. So you don't need to start from 0, because you can see that of course it cannot start with 0 1 and things. It's starting from this. So there is a good pruning that we have done over here, right? Around 1000 numbers got pruned as soon as we did this, right? Then fghij can be only up to 98765 by n. Now why is this? Because we know the numerator can only be up to 98. So the numerator is a 5-digit number which has all distinct characters. So the largest such number is 98765, right? The numerator is this. Maximum value of numerator is this. So the maximum value of denominator can be 98765 divided by n, right? So that's what we are trying to do over here. This is one more pruning that we are doing. So as soon as like n goes like large, let's say more than 10, this will be pretty large, right? Pretty small. Like this will get divided by 10 and the range will become very small. Make sense? So this is a nice pruning that we do over here. Okay, and then we do fghij plus plus, like we just try all possible values of fghij. Of course, there is a check that we need to do in this particular part, that okay, am I assigning distinct characters to everything? So we can just check, okay, let's say we can get the value of abcde equal to fghij. So first of all, you need to check this is the equation, right? This is the value of abcde, and then what we have to do is we will have to check for all the digits of the 10 digits that are there, 5 over here, 5 over here, whether all of them are distinct or not. So just you can simply do that using a set. There is more efficient ways, but let's simply take it with sets. Okay, so we know that to count the number of distinct characters or count the number of distinct numbers in an array, we can simply use a set. So just take all the numbers, all the digits of the number. So you can just keep on dividing by 10 and take the remainder 10, and that's how we generally know how we can take the digits of a integer. So just take the digits and insert it into set, take all the digits of FG, HIJ, insert it into the set and check if set.size, so st.size should be equal to 10. And then you like do a answer plus plus, right? This is something you can just check, right? After insert all, insert the two numbers and then check this. Make sense? So this is how you can do this. Instead of set, you can also use something called masks. So what you can do is, we have discussed this in bit manipulation a bit, but let's quickly recapitulate that. So what you can do is you can say that, okay, 0 is 0th bit, 1 is 1th bit, 2 is 2 bit. So for every digit you see, if it is 0, you mark the 0th bit of a number, like this is 0, 1, 2. You can mark the 0th, everything is initially 0. So if you see 0 in this 10 numbers, so you are going digit by digit, right? So for every digit you see that if it's a 0, make the 0th bit 1. If you see it's 2, then make the 2th bit 1. At the end, if all the 10 bits are on, then it's, you can say that, okay, it contains all the 10 digits, or else it does not. So it's a very small optimization, but it's something that you can do, right? So in brute force, sometimes these optimizations play a big role. Like it helps you to like prune faster. Okay? So this is something also that you should learn, because it's not always that you might be able to find out a very optimal solution for every problem, right? Be it in competitions, be it in coding test or interview. Coding test, at least in interviews that's true, but at least in coding test. So what you can do is you can use these brute force techniques to quickly write up a solution, and let's say just put it to pass as many test cases as you can, right? Because sometimes some companies have points on partial test cases, some companies in some questions you have partial points for some test cases getting passed, and so on, right? So these brute force really helps you in those scenarios. Okay, of course you might not get benefit of brute force in, like, at least in training purposes. Like when we set, we generally make sure that brute force does not pass us for the problem. That's how we design test cases. But in general, like when you solve questions for some other on some other platform or contest that is not that trustworthy, you can try brute forces if it's not working, if you're not able to get the solution. Okay, so mostly in internship coding tests or placement coding tests, this is true. Like sometimes brute force even gets you full marks, even though that's not the desired solution. But make sure so that's why we generally should know how to brute force efficiently, right? So you should try to solve it as minimum time as possible. Okay. So these are some pruning ideas that we talked about, right? This is just a simple iterative code which quickly enumerated on all possible solutions. And if you think about this, this is like this constant, this would be very small, this number would be very small. It would be in precise, if I'm just writing it currently 70 into, let's say, 10 to the power 5, but if you talk about how much distinct, what would be the different number of values, so you can say this is nothing but, let's say, 98765 divided by 1 plus 98765 divided by 2, and so on. So this is nothing but, even this is up to 70 only. So all these last terms are very small. So this is not even 70, this is something close to, let's say, 10 or something like that, because all these large values would be very small. So this is quite a small number, right, compared to 10 to the power 10. If you think about, we are doing something like 10 to the power 10, and then you directly jumped into, let's say, something like 10 to the power 6. Sorry, this is not 10 to the power 10, this is 10 to the power, it will be 10 to the power 8 around. It is around 10 to the power 8, but you can jump to 10 to the power 6 using simple optimization, right? So these are some things that you should like get into when you are writing brute force, that how do I, in what order do I loop? So we could have looped on A, B, C, D, E and F, G, H, I, J, and then checked that, okay, is it divisible? That's one order. Also, we could have like looped on A, B, C, D, E, and N. So you should, based on constraint, look into what is the order in which I should loop, so that I need to loop minimum number of things. Okay. So in general, you can keep this in mind that, okay, if I'm looping, the variable which is like the least constraint should be something that I derive. Okay. So it's like one that has the highest range of values that it can take. I don't want to loop on that. That is something I should derive through formula, and the other things I will brute on. Okay, something like that. Okay. So is this whole idea clear? Like what we have done in this particular problem? Is it clear to everyone? Can I have a +1 on the chat? So this is just simple implementation and all, but it's just how do you do that elegantly, right? Like how do you simply just prune it as much as you can, right? Okay. So next we talk about one recursive question. So this was one iterative. Iterative ones are comparatively, I would say, easier because you just have to write loops and something like that. Okay? So it's comparatively easier. Recursive ones are something that you need to be careful about, like how do you write the code and how do you like maintain the property of things here and there. So we will talk about that. So let's first start with very simple n queen problem. Uh, so I'll be implementing it, but in a way so that you can understand that okay, you can do the same problem in much more efficient ways as well. Okay. So I think how many of you have already solved n queen problem before? Let's say, can I have a +2 on the chat? I think some of you should have already. Like it's a very famous problem. Okay. Yeah. So you have a n cross n chessboard, okay, and you have to place n queens on this. So let's just take an example of 4. Okay. So we need to place n queens on this, and you need to find how many different ways are there to place n queens. There are different versions of this where you have blockades on places and other things, but let's say we just solve the most vanilla flavor possible, like just direct board and we need to place n queens. Okay. Now, so like if you think about this, one solution would be something like this. I think this works. Yeah, this works. Okay, so the one solution would be this. For 4 cross 4, there are only 2 solutions, one this and one of its symmetrical opposite one, like just flip it around this. So there are only 2 solutions for 4 cross 4 if I remember properly. Now with this n queen problem given n, find out the number of solutions. Okay, so the only input is n because you have n cross n chess, but there is no other input needed. Okay. Now the idea we use in recursive problems is first find some order in which you will be placing the elements. Okay, find order in which you place elements, order of move, I would say. Okay, so there are something like you are placing queens on the board, right? So find the order in which you will do the move. So let's say the order would be the most standard way. Okay, so the problem is there is a n cross n chessboard and you need to place n queens on the chessboard such that no queens attack each other. Okay, so there are only n different queens possible, right? Just yep. Is the screen visible back? I think should be. Yeah. Okay. So now you need to find the order in which we'll place the queens. So let's say we place it row by row. That's the traditional way. So we'll be doing that again, but again more elegantly, right? So one thing in competitive I would suggest is like when you are implementing, you should strive to learn how to do these things efficiently so that as you like, so the implementation part should take the least amount of time and the thinking part should take the most, right? So that's something you should pick up as well. Okay. So we will place things row by row. So what we'll be doing is we have a board. Okay. So I hope the question is clear that no queen should attack each other. So no queen is over attacking any of the other queen. That's the stating over here. Okay. So what we'll be doing is we'll be starting from the first row. We would place one queen and then we go to the next row. Then we check, can we place a queen over here? Can we place a queen over here? No, because this queen attacks this queen attacks this. Then we try to place the queen over here. So we place a queen, let's say over here. Okay. And then we go to the next row and we try out, okay, can we place a queen anywhere? So this is blocked due to this queen. This 3 cells are blocked due to this queen. So we cannot place any queen in this row. So what we say that, okay, this is not good because I cannot place any queen in that row itself. So we need to go back. Now note that if you have n cross n chessboard and you need to place n queens, of course you will have to place at least one queen in each row because we know that queens attack in 3 directions. So when you have on chessboard a queen is there, so it attacks diagonally, same row and same column, right, in all 8 directions. Make sense? So if you cannot place a queen in this row, then we are doomed and we don't have a solution anymore. Like there is no point in going any forward, right? We know that we cannot get a solution. So just backtrack. Okay, so this is something called backtrack. So this idea is called backtracking. That we try something, we try to do something, we go as deep as we can, and then we see that okay, it's not working. We come back and then we try some other move. Okay. So we say that, okay, we tried placing it all these places. Okay. So we placed it over here and we then placed over here. But we saw that when we placed over here, we could not place anywhere in the next row, right? So we come back, we remove queen from over here, and then we place the queen over here. Okay. And then we try the next row. We see that, okay, this cell is attacked by this. These two cells are attacked by these, but this is free. So we try to place a queen over here. Okay. And then we see that, okay, there is no square possible. So we then track back. So we say that, okay, there is no room for this. Again, in this particular row, we have tried all the possible positions, right? We tried this and this are anyways not possible. We tried this, but we got no solution. Then we tried this, we got no solution, and then we tracked back. Then so after this, we track back 2 rows, like none of the moves are possible. Okay. Then we just also remove this and try the next move. Okay. So if you think about the board, now the board would be something like this. So we have removed this queen from this, and then we try the next move in this row. Okay. So for every row, you have some moves. Okay. So you can place either here, here, here. Some of them might not be valid. So we try one, go to the next row. We try to place the other queens. Then we come back to this row, remove queen from this position, try the next position, and then go into the next row. That's what we are doing. So then again, come back, remove this, place over here, come back, remove this, place over here, come back, remove this. And then when we see that, okay, there are all moves done in the first row itself, then we are done with all enumerations possible, right? So this is what we are doing in the whole recursion part. So this is what we're doing in backtracking. So we'll be implementing it using a recursion that, okay, we will place it in this row and then we will recurse on the next rows. Okay, so we will look into the recursion part when we code this up. But is the idea clear that what we are doing over here? Like placing the queens, go to the next row, try to place over there. If we don't have a solution, come back and try the next move in that row, in the previous row. Okay. Of course, you will have to keep track of the queens placed in all the previous rows, so that when you are trying to place the queen in this row, you will have to check, okay, if I want to place it over here, okay, this queen is attacking me, so I cannot place it over here, right? If you want to place this, okay, this queen is attacking me, so I cannot place it over here, right? So this is something you have to keep track of. So everything that we placed till now, we'll have to keep tracking of that. But in recursion, we can keep track of that. Okay? So is the idea clear that what we are doing, what we're trying to do? Is it clear to everyone? Can I have +1? I think next we will directly moving to the code, and I'll be explaining the rest of the stuff through code only. Okay. Okay. So let me see. So we'd be like, let's say we'd be taking n and we would be solving the n queen problem for that instance, right? So just a second. So we'd be using a simple vector for this to store the previous placed queens. Okay. Okay. So I'm writing the variable names a bit cleanly. I will try to keep it as much clean as possible. But in general, when I implement, I don't care that much of variable names. So, so let's say we have placed some queens in the previous row, and then we will keep track of those in a vector. Okay. So this is the best thing about recursion, that you can maintain global level variables along with recursion. So I will explain what I mean by that. So I will also have, like, let's say answer variable, which will count the number of solutions that we have got till now. Okay. Okay, so then let's call it recurse. I'm just writing it. Okay, that's recursion. Okay. So which row we are placing the queen right now in, and that's the only parameter that I will pass. Okay, this is the row in which I'm trying to place the queen. Okay. So that means what I'd be doing is I'd be just calling recursion of 0. So I'd be starting at the row number 0, and when I reach n, I'm done. Okay, so I need n to break off. So out of these, I will say that, okay, let's say if my row is equal to n, then answer plus and return. I'm explaining what I'm doing. So what we'll be doing is, we have the board, right? So this is row number 0, this is row number 1, row number 2, row number 3, and n is equal to 4, right? When we have 4 size board, the n is 4. So we try to place a queen. We place a queen over here. Let me complete the board. we place a queen over here. We come to this row, we place a queen over here. We come to this row, we place a queen over here. And then we come to this row, we place a queen over here. And then we come to this row and we see that we have reached the row number 4. So that means all the previous row has been like successfully placed. The queens in the previous rows has been successfully placed. So now we can say, okay, we are done. And like this is one possible configuration. So that's answer plus plus. If you want to store, you can store the positions of the placed queens. Okay. So what is this place that we are maintaining? I'll be explaining that as well. Let's say this is the like a vector that we're storing. So this is 0, 1, 2, 3, 4, and so on. Okay. These are the positions. There will be up to 8. Okay, this is the vector that I'm maintaining. And 0 will contain 1 in this case because I'm storing it in column number 1. So the queen in the row 2 is placed at column number 3. The queen in row 2 is placed at column number 0. The queen in row 3 is placed at column number, so this will be up to 4 only for this particular instance. In the column number 2, right? So this is how my vector will look when I come to this particular recursion, right? So I would be pushing the column number in the vector, and anyways the index of the like vector will give me the row number, right? So that's pretty neat to keep, because anyways this is the position of the queens if you think about it, right? Nice. So this is how we are maintaining things. So that's this vector that I'm keeping with my code. Okay. So let me quickly draw that over here as well. So this is, let's say 0, 1, 2, 3, and I will maintain this. Okay. Now, so when we reach this particular row number n, we are done. Okay, so we make an answer process and we return. So this answer is counting the number of times we have reached row number n. That's the number of solutions, in fact. Okay. Now, if it's not row number n, then we have to place it somewhere. So there are like n number of columns to try in, right? So let's say this, let's name cleanly. So let's say we want to place it in some column. Okay, so in this particular row, we will try all moves in sequential order. Okay, so we'll try to place it in column number 0, then we will try to place it in column number 1, and so on up to n. Okay. Now, before placing the queen over there, we need to check whether like it's getting attacked with some other queen or not, right? So we'll say something like this: bool safe. Is it safe to go over there? So is it safe to place the queen over here? Okay. And then what we'll do is we will loop over all possible. So we will loop on all previous rows where we have placed the queens by now. Okay. And we need to check whether that previous queen is attacking my current queen or not. So this particular, so if you, okay, let me just write previous column as well. So previous column would be nothing but placed of previous row. Okay. Right, previous row. Makes sense? So these are the two coordinates. So what we are trying to do right now is we have, so in the board, let me remove this board because anyways this is like a done state. So when we are talking about a board, so we are at some particular row. Okay, so we are considering that can we place a queen over here at row comma column. Okay, given that there is some queen at some previous row at p row comma p col. Okay, makes sense? So there are two things. First of all, of course, we know that the rows don't coincide. So we don't need to check the row condition of queens that either the row is same or not. Okay, we just need to check the column and diagonals. Okay, so how do we write the, so columns is pretty simple. If previous column is equal to the current column, then like safe is equal to 0 because it's not safe to place a queen over here, right? Or would be some other condition based on diagonal. Now, how do we write the condition for diagonal? Okay, so simply you can write it something like this: if abs of row minus previous row. Yeah, exactly. That's a more elegant way to write it. Abs of row minus previous row is equal to abs of column minus p column. I'll be removing this a bit. Okay. So if abs of row minus p row is equal to abs of col minus p previous column. So this is basically like either plus 45 or minus 45 if you think about that. Like what this means, either slope of 1 or slope of -1 basically, right? So we are using some sort of slopes. So if this is true, then that means there is a diagonal attack, so we cannot place it, so it's not safe. So if it's safe, okay, then we try to place the queen at that position. So what we do is we do place dot pushback. We place the queen at this position, so we place at current column that we are considering. Okay, then we go to the recursion for the next row, and then we do a place dot pop back. So we remove the last placed queen, and then we try the next moves, and that's it. That's the whole code for n queen. Okay. So no need to keep 2D boards and all to implement n queen and other things. Just simple, this much code should be sufficient enough. Okay. And then if you call rec0 and then we, let's say, see out answer, let's look into if we are getting the desired numbers or not. Let's say for 4, yeah, for 4 it's 2. For 8 we know it's 96, 92. Okay, 92. Yep. So that's working correct. So the code is correct, right? Is this the most efficient implementation? No. So this can solve for n queen up to, let's say, so let's talk about its complexity first of all. What is the complexity for this? Like, can somebody maybe guess what the complexity can be? This is simple. Like, this is not very difficult. So what is the complexity for this particular thing? So you are placing queen, then in the next row you're placing queen, and so on, right? What is the complexity? N square. N factorial seems much better. N square, not n square, right? So for first one you have n choices. For the next one you can say that, okay, the same column gets removed for sure. Okay. For the next one it's like n minus 2 factorial and n minus 2 choices and so on, because anyways you are removing the same column, right? So it's actually n factorial. To be precise, the actual complexity is actually something called n double factorial. So there is a notation called double factorial, which means this: n multiplied by n minus 2 multiplied by n minus 3. So at least one diagonal also gets cancelled. That's like a thing that you need to understand. So every time you, sorry, this 4, right, n minus 6 and so on, like every 2 difference from n, that's what is called n double factorial. Okay. So its actual complexity is n double factorial, but you can if you say that it's n factorial, that's perfectly correct. Now this is like asymptotically, that's quite good enough. Yeah, yeah, we can use even an array. That's perfectly fine. Like, yeah, that if you have a fixed array size of n, that's also fine. So the main thing that I wanted to tell in this particular, why I implemented in this way is, so use this particular style of construct when you're implementing, if you are like fresh new to like brute force, that when you're adding recursion, first there comes a base case where you see that, okay, you come to the last row, you have made all your decisions and you have now reached some state. So either this will be direct answer plus plus, or you will check that, okay, whatever I have placed, is it satisfiable or not, something like that. There is a check or like increment, something like this in this base case part. Okay. So based on check, you can either increment, or you say that, okay, this is not a suitable solution for me, and so on, right? This is how you implement the base case part. Okay. And if it's base case, then you return, or else you try the moves in this particular row. So over here, you enumerate on moves. Okay. Now, for every move, like you keep like, is possible, some sort of is possible check. Is that move even possible? Is the move possible? That's what we are doing in this whole part, right? We're checking whether that move is possible or not. And in this part, we have 3 portions: do the move, move to the next row, move to next choices, and then remove the move. Okay, so always follow these things. So it's just why, because we wanted to remove the contribution, that's why I just made it pop back. You can even keep like a 8 size vector and just keep it with that, like whatever the maximum dimension is, it's perfectly fine with that. Okay, so you just need to keep something like -1. Even you don't need -1, you just can put the value and then loop into the next part. So this is the whole construct that you should follow, that in base case, check whether it's working or not. Enumerate on moves in that particular like state that you have, okay, and whatever move you have. Is it possible to move whichever move you are considering? Is it possible? Based on that, it's possible, if possible, like this is some check, or else we could have implemented this check in the after going to the recursion as well. But let's say we're checking before going to the recursion. Okay, that is it possible or not? Some quick check. Okay, then do the move to the next state, and then like if after you are done with searching in the next state, come back and remove the moves contribution, and then try the next move. Okay, that's the whole construct of any recursive backtracking code. Okay, is this code clear to everyone? Like any backtracking code can be like thought of in this particular style. Can I have a plus on the chat if this is clear to everyone? Any doubts on any part of this? Okay. Okay. So now we'll be talking about one more problem. Pop back. Okay. So this is nothing but something like this, that so in vector you have a function called popback which can remove the last element in vector. Okay, so in vectors it's like one-sided DQ, so you can even put one element at the back and then you can also remove one element from the back. So what I'm doing is initially it's empty. If I place a queen, I place like something like, let's say this is the, so I place it at column 1, in the next row I place it at column 3, in the next row I place it at column 0, in the next row I place it at column 2, and then when I need to remove this column 2, I just pop this element and so on, right? You can also maintain an array, that's possible. So sometimes when I need, I generally use vectors to implement stack itself, because vectors are quite self-sufficient to implement stack. So in normal stack that you have in STL, you generally you can't access the elements inside it, right? But in vectors, you can also access elements in any ith position, as well as you can push back and pop back, right? So if you think about this vector, something like this form, then you have like a stack, all the stack operations possible. Make sense? There is something called place.back, which gives you the last element of the vector. Okay, so it can support everything that's a stack can support, and along with that, you also get a functionality of like having any ith index. So you can also use vectors in place of stacks when you need to implement. But so anyways, this is some sort of stack that we're implementing. That's it. Make sense? Is this clear, Aditya? Yeah. So you can also create, like as Vijay suggested, you can create like a separate like dynamic sized array, like whatever the maximum size of n is. That's also possible. Okay. Okay. So next we talk about another problem. So let's go back to the front board. Okay. So now let's talk about one more problem of, let's say, so let's talk about one more problem of brute force. Let me just quickly open it. So we will take up one problem for, let's say, kickstart, which happened recently. I did not participate, but I happened to look at the question, so maybe we will look at that particular question. So the recent round F had one question, painter's duel. Okay, so we'll be taking up this particular problem and we'll be solving it. You said you can have more elegant solutions. Okay, yeah, we can have more elegant solutions using something called bit mask. So the diagonal checks can be efficient. Like I can give you a quick hint. How do we have more efficient solutions? So you can maintain like some bit masks for columns, like which columns have been taken up, a bit mask for which diagonals have been taken up in the board, and a bit mask for which right diagonals have been taken up, and the and like or of all these will give you like will quickly give you the number of like which all positions are possible. And if you flip that and just iterate on all once, so that will give you like the quick, you will get quick access to all the positions that are only possible. So that's like a quick efficient prune that you can do, but we'll not be going into the implementation because this will become quite like difficult for now. Okay, so this implementation is a bit difficult, but the thing is like if you say that okay, like in the current row, this diagonal like which ends at this row, this column diagonal, this and this diagonal is blocked, right? Okay, some by some queen. Then in the next row, this position will be blocked, this position will be blocked, and this position will be blocked, right? So it's like in this row, if you have some mask which shows that okay, which right diagonals are blocked, in the next row that will be nothing but mask right shifted by one. Okay, so something like this we can implement with some bit masks and all. So there will be 3 masks that we maintain along with recursion, but that's a bit difficult, so we will not be looking into this solution right now. Okay, so you can look into, so this particular solution allows you to solve it up to let's say 18. So you can solve up to 18, n equal to 18 with this particular solution. The normal that we discussed one like will work only up to 12 or maybe 14. That's how much it can work. Okay. Okay. So coming back to this, so let's talk about what we have. Okay. So there is a maze, something like this. Okay. This is a problem from the like last kickstart, so you can have a look at it later on. So the question is, you have a pyramid styled rooms. Okay, so this is how it's named, it's numbered, that first, this is the first row, second row, and third row, right? So you can divide it into equilateral triangles, and that's each of the equilateral triangle is a room. Okay, and from each of the rooms you can go to 3 of its neighbor rooms. Okay, now there are 2 artists that start. One starts at RA PA, like row A and some point A, and row B and point B. Okay, like say 2,1 and 3,5. Okay, and based on that, what they do is when they start, say first will start. So there will be the first player over here, and second player, let's say, is over here. So the first will start and move to one of its square that is like not yet visited, and will mark it that as its own territory. Okay, so initially these 2 are its own territory. This and this is this node's territory. Okay, so it will go to one more and mark it as its own territory. Okay, then it will be this player's turn. He will walk to one of its neighbor and mark it as his territory. Okay, then it will be his turn. He can go to one of its neighboring cell that's not yet visited. So to this, let's say so this will be, let's say this will be 2, this will be 2, sorry, this will be the player 1. So let's number them with player number. So this was player 1, so this is player 1, this is player 2. Okay, then player 1 moved to this cell, so this cell is now player 1. This player moves to this cell, so this is player 2 now. Then this player moves to this cell, this is player 1. Then this player moves to this cell, this is player 2. Now as you reach this cell, you cannot go to any cell which is not yet visited, right? Like this is already visited by player 1 and this is already visited by player 2. So then any player who cannot move loses. Make sense? So any player, once both players are unable to move, the game is over. The score of the game is the number of rooms painted by A minus the number of rooms painted by B. Okay. Now both players makes optimal decisions when Alva tries to make the so of course, like this player stops over here. Now this player can keep on moving. Now let me go back to this diagram. Right. So this player, so this, you cannot move from this, but this player can go to this, and it will capture all these cells. So it's like somewhat like a capture flags or something like that. Okay, capture the rooms, some sort of that green. Okay, and based on that, you need to decide on which, like each player plays optimally. So you will need to decide on what will be the best that the first player can do. Okay, so like Alma wants to maximize the score, and like the score is Alma scores minus Brett's B score. Okay, A score minus B score. So Alma wants to maximize his score, like the difference, and the other one wants to minimize, because that's what it's doing, right? They own individually wants to maximize their own score. That's what they are doing. So given this, given this, determine the best score Alma can guarantee for the game, like the best score first player can do. Okay, that's what we need to find, regardless of what like B does. Like B will of course try to minimize it, and A will try to maximize it. So out of all possibilities, we will try to find out the best move. Now, when you look at this problem, this seems quite a difficult. Like, what is like? First of all, this cell diagram is in itself a bit like difficult to understand directly, and the second thing is like it's quite a complex game. It's not something like there is no rule direct to decide on which can win, right? So if you look at the constraints, the good thing is that first constraint says that S is equal to 2, which means the number of sides of this triangle is 2, which means that the triangle will always be of shape. That's the first part, test case, that it will only always be like this. Okay. Now also out of these cells, some of the cells can be blocked. That's also given, that some of the cells may, like C of the, each of the players are starting at C of the rooms of the museum are under construction. So it's like they cannot be used. Okay. So for the small test case, it's like something like there are only 3 cells, and from this you can like brute on how much one can get. So this is very easy. You can write if else code for this if you want to, but we would try to solve the general version, like this larger one. Okay, which is, let's say you have to solve it for 6-sided. Okay, so there is only 6 by 6, like there is a 6 splits into the triangle, and we need to find out, given the starting position, ending position, the positions which are blocked, find out which cells can be what would be the maximum score for the player 1. Okay, that's what we'll be trying to find. And so this is for 2-1. So it's like this is the same as one of the examples that we discussed. That's nothing in there. Okay, so this is the whole problem. If you want, you can open up the question as well on your laptop in case you want to quickly refer to sample test case or something like that, to the statement in between. So we would be implementing this. This would take some time, but I really want to implement this so that you get to understand, okay, how should you implement these type of problems and such game scenario problems, and of course some optimization on how do you write these things efficiently. That's all, because these are some things that you should pick up now. Okay, so I have not already implemented it. I did not participate in this particular start, but let's look into how we can do this. Make sense? So let's look into how we can implement this. Okay, so of course we have some 2D kind of rectangle. There is a 2D kind of structure that is given in the problem. So how do we represent this? So of course it's very difficult to like directly keep something like a triangle. So we will like make it skewed. So we will have something like this. So there is 1, there is 3, and then there is 5, and so on, right? So we will make it something like this because it's difficult to implement a triangle in structure, right? So we will store it something like this because that's easier. Okay? And we anyways have only 6. Okay, so there are only 6 rows and 6 columns at max. Okay. No, so the number of columns can be up to 2n minus 1, right? Because there is like for 3 there is 5, so it can be up to 2n minus 1. Make sense? So this is how we'll be implementing the storage part. So let's start with the code. I think take some time, but I think this is important. So we are given the side length. I think there is position. Let's check what are the parameters. I get the browser. Just position it a bit. Okay, so there is position A, position B, S, and RA, RB, and C. These are the inputs. Okay, so we will take that up. So we have RA, PA, RB, PB. Okay, and this is how even I would have implemented if I would have been giving the contest. So S, RA, PA, RB, PB, okay, and then the C, that's the number of blocked cells. And then we will need something, let's say, like which all cells are currently like blocked. So we will keep something like int allowed, let's say, okay, allowed to move in this place or not, something like that, okay, which all cells are allowed or not. Now allowed would be, let's say we keep just 10 cos 10 because anyways it's just 6, so it's not going to matter. So I generally have a habit of keeping some more spaces. That's just so that in case I switch to, let's say, from 0 indexing to 1 indexing or something like that, I don't really get a sec fault. Okay. So now let's quickly, so since the question asks for test cases, okay, case 1, case 2, so we will print the cases later on. So let's say we just size of allowed. So memset works with 0 and -1. So we just use, like, it's all initially allowed. So allowed 0 means like it's not blocked, okay, and 1 will mean that it's blocked. Now, of course, there are C inputs which all cells are blocked, but along with that, the initial positions where like they are present, they are also blocked, right? Because they are already marked, and you cannot move to something that's already marked. Okay, so allowed of let's say RB and PB is also equal to 1 because they both are blocked. Also, we have the inputs of the cells which are separately blocked. Okay, so these are all blocked, and then we will try to implement something called get best. So let's just print cout get best, like what is the best score that I can create when I start with RA and PA and my opponent starts with RB and PB. Okay, that's all we want to just pass, because that's, so here we have to decide something which is called states. So I'm thinking, when I'm thinking about how to implement this, anyways, this allowed will tell me which all cells are things that where I can move into, right? So I just need the current positions of A and current position of B, and based on where I'm allowed to move, I will move in that direction, right? So I will enumerate on all possible things, and based on that, I will just decide. Okay. So, and that's the brute part. Okay. So we will need to implement this get best, right? So how do we, like, first of all, implement this? So we will implement two things. First thing called check. I'm going to explain what this is, and something called get best. Okay. Now, when I generally try to move from a particular cell, I can go in three. Yeah, I'm going to explain that. So when I move from a particular cell, we generally get we can go into three neighbors, right? But in case we are at the border, some of the neighbors can go like outside the cell, like outside the range. So that, just to check whether some integer x comma y is inside the bound or not. Okay, I'm just implementing this check function. Now inline is just quick optimization, because I'm going to write, generally this check function that I write is of 1 or 2 lines. So with inline, it gets into the places where it's relevant at, so just a bit faster. That's it. So these are something that, like, I have built a habit of using while I'm coding, but that's something you can ignore as well. Like, it's okay if you don't write inline, that's perfectly fine. And so of course both of them needs to be greater than equal to 1, and x needs to be, the number of rows needs to be greater than equal to, less than equal to s. The column should be less than equal to 2x minus 1, right? Yep. Y needs to be less than equal to 2 into x minus 1, because if you are at the xth row, then the number of column cells is 2 and minus 1. We discussed this. So 2x minus 1. Okay. And if, so we will check, can we move to x comma y, right? So if allowed of x comma y is equal to 0, then only we can move there, right? Then only we can, like, it's possible to move at that place, or else it's like it's uh, not possible to move there. Okay. So this inline will do, what it will do is it will take these two lines and place, like, use, while compiling it will place it at that places where it's called. Okay. So now what we can do is, we have the two positions. So let's say the first pair is at position a comma b, and the other one is at x comma y. Okay, so these are the two positions. Let's say we will try to store the possible positions of where A can go to and where B can go to into let's say vectors. So this is how even I generally implement. If you, we will discuss about graphs and other things, but even if you think in graph, this is how we will generally implement as well most of the things. So when we are doing some sort of search, we will try to, like, for every position, we will try to find out where all we can go to, right? So let's say where all the first player can go to. Let's say move 1. Okay. Similarly, I can have another one which is move 2, like where all the second player can go to, right? Vector pair into move. Yeah. So these are the, so every position is x comma y, right? Do you remember the priority of these x and r operator? Yeah. So less than equal to are like evaluated first. So the priority is like and is evaluated first, like first less symbols, then ands, and then ors. Like and will get evaluated first before ors, and so on. So these things you learn when you make bugs. So I have made bugs due to this, and now I remember these things. You can put in brackets if you want to. Okay, so I have learned through making bugs only. Like it's no exception there. I have made bugs in some problem where I did not put in bracket, and then I got wrong answer, and then I understood that okay, I need to put brackets, or I then know that okay, or is evaluated for with that. That's how I retain it for much longer time duration than just reading it from some book. Okay. Because anyways, you won't be remembering the order from by reading books, right? Okay. Now the main thing, where all can we go to from a particular A comma B? Now that's something difficult. Okay. So for any cell A comma B, we can go to A minus 1. So of course we can go to previous cell and the next cell in the same row. So we will try to use that first. Okay. So if check of A, so in the same row we go to B minus 1. Okay. So if we can go to that cell, then move 1 dot. So let me, okay, let's not go into too much of optimization, because then, okay, let me. So this is something I personally use, so that's why. So I generally prefer emplace back over pushback. I will tell you the reason. So I can go to the previous column or the next column, right? These are the two things. Now, emplace back is a bit faster version of pushback, but it also comes at a cost that you need to write make pair over here. If you had written like something like pushback over here, you could have worked with some syntax like this, right? So this is a valid syntax, but if you use emplace back, then this is not a valid syntax, and you need to use make pair. Okay. Okay. So I generally have like shortcuts made for, if I just quickly, let's say, talk about things that I have in general templates. So I generally create like these make pair as MP and emplace back as EB, so that I just need to write EB and MP so that I can just write. Not in every problem, but maybe in 1% of problems that I solve. Sometimes out of every 100 problem, maybe one might get affected due to this. Like if you're, I think at this stage does not matter, but the type of problems that we generally work, like we generally work on different, not in brute, in even different other like advanced algorithms, like when you write long algorithms and you need to try to keep the codes in between as well, with as much efficient as possible. Like even if you are implementing some long algorithm like FFT or flow or something like that, but you need to try to keep things in between as cheap as possible, because that might be called again and again. Okay. So if you're inefficient in a lot of places, then in total it might get to a wrong answer. So one more pointers I would like to give you all. I think this I have checked once, so this is out of the context right now, but when we are printing, make sure you don't use endl from now on. Okay. Don't use endl, or if you're habitually using endl, use something that I use. Define endl as /n. Okay. endl is very slow compared to /n, and if you are printing, let's say 10 to the power 6 lines, and if you use endl in all of them, you might get a TLE. Okay, so get a habit of like either writing /n, or if you are using endl like me, I generally use endl. So I have endl defined as /n in my template, so I generally don't care about that now. Okay, but I know, but in back of my mind, I know that if I'm getting a TLE, I might get it for endl, but you might not know that, right? So that's why this heads up that okay, in endl, if you're using endl, if you're getting a like, it's okay if you use endl, but if you're having a like a heavy IO, like input output, and if you're using endl and you're getting a TLE, it might be due to endl. So it's better like quickly use /n in that. Okay, that's just a quick heads up. We don't need it for this particular problem because you're just outputting one number, right? If you're outputting a large number of numbers, then it might be relevant. Okay. So move one dot emplace back, these two things. Now we want to go to some top row, like based on where we are, we need to go to row, like column above it or column below it, right? So if my row number is even, then I can go to bottom, like I can go one step below. And if my row number is odd, then I can go one step up, right? So if we can also say it in this sense that if my column number is odd, I can go below, because anyways in row we have alternate signs, right? So if you see every odd number from every like x comma odd number, we can go down, right? Every x comma odd number we can go down. So if b mod 2, if b mod equal to 2, if b mod 2, so if we can go to else, right? So let's say if b is even, then we can go to a place that is above, right? So we need to check the row before that and b minus 1, because from 2 comma 2 you go to 1 comma 1, right? So it's like the when you go from 3 comma 4 you go to 2 comma 3. So b is also decreasing by 1. So this is the cell in which you will lead to. So if we just check whether we can go to that cell or not, and we just like, if we can go to, then we just emplace back that. Okay. Make sense? Again, when you are in let's say some of the downwards one, so your column increases, right? When you are in downward one, your column number increases, right? So you need to check this particular position, and this would be k plus 1 because you are going to the lower sphere, right? So is all these three moves clear? Like there are only three moves from to which a particular cell can go to, and based on these conditions, I have created a vector on which all cells I can go to from a comma b, right? That's all I'm creating right now. These are the potential moves. Remember our brute force strategy that we first need to enumerate on moves possible, right? So for that, we need to first of all find out what are the possible moves, and this is what we have done till now. Okay. Now there is a base, so we have not written base case yet, right? So we need to write base case. Now how do we decide on base case? In the question it's given like when both of them cannot move, once both pointer are unable to move, the game is over, right? So when both their moves are empty, that means we are in the base case. So I will have to also create the moves of the other player. So I will quickly copy this and I will replace all a's with x. That should be sufficient. So you can copy this, replace all move ones with move two. Okay. So a will, so x, okay. And then all these b minus ones. Okay, so we are missing something. This is the trouble when we use uh, when we use copy and pasting, make sure you are like doing it correctly, right? So this x plus 1, x plus 1, x minus 1, x minus 1, x all x are, this is somewhere we left it. Okay. these all would be replaced by y plus 1. Makes sense. I think we are done with this part, right? Yeah. So these are the two parts. Nice. Okay, so in Sublime you have, like, if you select a particular string and then you write command plus control or command plus B, then it, sorry, that's the build part. Command plus, what I was using, command D, yeah. Command D, then it goes to the next, like it keeps on selecting the next occurrence of the thing, of the particular selected string. Okay? Control plus D or command plus D. So it keeps selecting the next occurrence of the string. So that's a Sublime specific, I think, shortcut. Move to would be good. So it generally helps with when you can't use find all, right? Because there are previous appliance ones as well. Okay, so now if now we have all the moves possible, like in the both the players. Now if now we write the base case. So this is some quick pre-computation that we did. Move one dot, if move one dot empty. Now we are writing the base case. Okay, if move one dot empty and move two dot empty. So if both of the player can't move, that means we are at the end of the game, right? So now the next scores that we can create is going to be 0. Now let me explain what we are returning from this particular get best. So get best would be the get best score. That is nothing but the difference of, like, the number that we are talking about. Like there is a score defined, right? Get best score. This function is get best score. Okay, that is the difference of the first player minus the second player. Okay, so that's what we are returning right now. If both can't move, we return 0. That's the base case. Or else we have some move. Okay, else if move one dot empty, if we have some move for the first player, like if the first player's moves are not empty, then we can enumerate on those moves, right? So there are at most, let's say, something around 6 square or something like that number of squares in the board, right? Some sort of like that. See, something like that. 2s square minus s square minus 2, yeah, that many cells are there on the board. S square number of cells. Okay, so let's say so this is nothing but the count of number of rooms, right? So we can just initialize it with, let's say, very large negative number, and we will try to maximize the score from the current position, right? So whoever move it is right now, we will try to maximize that player's current position's move, right? Like what is the maximum score he can create. So this is very important to understand that we are creating, let's say it's player A's, like player one's move and player two's move. So if it's player one's move, let's say his score is A and this score is B, so he wants to maximize A minus B, right? Yeah. So if none of them can move, after all of these, like what I'm doing is I would be keeping track of scores that I get, like +1 for this, +1 for this, and then when I reach this, if I hit a termination condition, I will return 0. So that means after this, there are no scores added to the total score, right? Now in the path, when we are writing the recursion over here, we will add the scores for any move that he makes. Okay? So when we hit the end, we say that, okay, no more scores after this. So whatever you have compiled till now, that's the answer. Okay, and that part will be written in the recursion. So we're coming to that. Okay. So we are just storing this different. Keep this in a note. Keep this in note. That's good. Now for auto, say v in, so we can be a sneaky. These are some optimization that I'm trying to talk about in between. So like ampersand v, like moves on the elements of things, like it moves on each of the elements of the array. So it's like something like a reference. So it does not copies into a variable. So if you write auto v in b without this ampersand, it generally copies it into a variable v. So if you are passing something to functions, and if you are not changing it, make sure you pass it by just by like ampersand, pass by reference. So now allowed v. So if move one is allowed, then what we do is, before moving to that position, we first of all make it blocked. Okay, so we make it's like that particular cell as blocked. Okay, so that becomes 1. So it becomes blocked. Sorry, this should be equal to. Yeah. Now that becomes blocked. Now go to the recursion, and then after coming back, make this again 0. Like it's now free. Okay, so this is how we generally write recursion. Okay, now we want to go into the recursion. So my player will go to v dot first comma v dot second. Now here is the trick of implementing this kind of function, because this will help us a lot now. Why? Because note, whichever player is first, we get the score of that particular player minus the next player, right? So what I would be doing is, I would be just calling, we will just take a max of all possible moves. Okay. So whatever the current best is, out of that, this player gets one move, one score, minus get best if the next player is now the first player. Okay. I will explain the expression just and so okay. So what I'm doing over here is, when I play, I from a comma b go to v dot first comma v comma second, I get a score of 1, and then I make the opponent, like the next player 1, and I call get best. Now this get best will try to find out the optimal choices for the opponent, because that's what the opponent has a call on, right? That's your opponent will also play optimally. So when you get to some x comma y, his player 1, he will play optimally for him, and that will basically give you some sort of, like, let's say you get a score of 1, and then your opponent plays gets some x score, and you get y score. So if you open up this minus over here from this get best, so it will get to like y plus 1 minus x, right? So it's like whatever your opponent does, based on that, whatever you get, it gets added to your score minus your opponent's score. So this is something getting maintained in this form of expression, right? Make sense? So that's why we have tried to keep it in like both the player 1 and player 2, so that we can quickly swap it over here and like have this difference equation being used to get to the actual sum of the difference of the scores of the two players, right? So this is like a small trick that I use to like to make my implementation life easier. Like that's it. Because or else I would have to keep like 2 counts of player 1 and player 2 and so on, and whose move it is. So too many parameters. Why to think of that much, right? You generally want to keep the things over here. Okay, keep things as small as possible. So you can keep like a separate variable, because anyways this is recursion, so we are not storing anything. So you can keep as many recursive parameters as you want to, but we want to be as much optimal as possible. So you can like if you want, you can keep like something like player 1, player 2, whose move it is, what is score 1 player 1, score 2 player, score of player 2, and so on. So that's too many variables to handle. Instead, just simple implementation that can help you with implementing these kind of problems, right? Any game where you need to make difference of things, you can simply use this kind of functions which maintains the difference. Okay. Now out of all these things, we just return the best for the current player. Of course, that's the best for you. Or else if you cannot move, then the game switches and you return the get like negative of, so you make 0 moves, so your score is 0. Next your opponent will make moves, so your opponent is at x comma y and you are at a comma b only, right? So you remain at a comma b, you cannot move anywhere. So it's empty, like your moves are empty, so your opponent will make a move. Okay, make sense? So I'm not really sure if this is correct. Let's quickly test on the sample. Sure. So okay, that's good. Okay, we have not activated test cases, and for every test case we need to print cases equal to something like that. CC plus plus. That will print the answer, and after that you solve the question, and then the solve prints an endl, so you will get to the next line. That should be sufficient. Yeah, it's giving 2-0. So that's great. I was hoping that I might make some mistake and need to recode it. I hope it's not. Let's submit it. check for quick errors. So it's generally I when I submit, I just either move to the next question, or I like quickly look into if I made a silly mistake on the code or not, so that you don't waste at least time when it's judging, right? Okay, yeah, so that's correct. So just a quick heads up, like if you could have solved this particular problem, let me like just do this. I looked at the ranks. I think uh, so this doesn't take much of time. If you could have solved it in decent amount of time, you could have just ranked within like 200 or something like that. Okay, so and taking a brute of the last question, so that's perfectly possible. So like getting a good kickstart rank is like good enough if you're trying to get into Google or something like that. So they look at when you if you're sitting for intern or something like that, you can try to do this. So giving kickstart is good. You can start giving kickstarts from now on. Okay. Anyways, but the times are quite odd. So this was in morning. I think that's why I did not give it. Because I thought for the problem. It's not like so I could not think of anything, and the constraint was small enough. So like it was 6 only, right? So I'm pretty sure that there would not be like more than 6, a lot of moves. Every time you have 3 moves for every player. So there is like 3 into some 3 to the power some number, right? 3 to the power 9 or 10. It will terminate very fast because the one player will try, in optimal sense, one player will try to restrict the other one. So it, in a lot of senses, in a lot of moves, you will get restricted very fast, because if you quickly get into some position where you cannot move anywhere, so it's just like just calling one option. So it will be very pruned. It will be pruned very fast. So like it's so if you're not getting some idea, you should try to implement brute, right? Like anyways, this constraint was quite suggestive that okay, it might be a brute. That's why I thought this might be brute. But in general, like if constraints are high, then you cannot do this in brute sense, right? Makes sense. That's how even I think like that there is no direct way to check if either if you can like count the exact number in like if you look into analysis, they might have given some bounds on the number of moves. So the total initial configuration is 2 to the power s square, which seems to be the yeah. So this is the thing, right? This is so they have also not given the exact count, but like with pruning, a lot of things gets like removed, right? So we are doing quite good amount of pruning only, and the code is fast enough. We could have done so. Can someone suggest me what else we could have improved on in this particular code? There is one possible scope of improvement that I just now thought that we are repeating in some sense. So basically, you are calculating moves too, but you're not using it, right? And then you are like switching and then again calculating moves one for the next player. So what you can do is whatever move two you calculate, you can somehow pass it to the next function and say that okay, this is move one for the next player, right? So that you can use if you want to, right? So you can have two parameters over here in the function itself, which can find out. Okay, so when first player moves, so it will be just like a check, right? So when we even when we have the like there is some checks that we are over computing, right? So yeah, of course there will be some changes, but still like it can be some order one optimization that you can do, like some of the moves will get removed, so a lot of like checks would be saved. So it will be just at most one square can get removed from all the 3 squares, but anyways it's just 3, so it's not a big optimization. But anyways, all 3 you don't need to check now, right? So you know that at most one can get to. But anyways, that's like very small optimization. Some things we can do here. Yeah, we can add moves to yeah, we can do that in fact. So we can kind of switch players, and so that's what we are doing right now. yeah, if we can think, yeah, so we can just, so there are a lot of options that you can think about when you're writing brute force, but it's just that, like, how do you write? Okay. uh, so I think this is one style. So I hope, like, I was first thinking whether we should do this or not, right? Whether we should code live on one question or not, but I hope like this particular thing helps because you get to learn a lot of different syntactical things, right? And these small things you can pick up because these are some things that I have learned through making mistakes. So no point in repeating them, right? Okay. Okay. So I think that's all for this question. Then let's move to the next one. Is everyone clear with what we did, what all we did in this particular question? Everyone clear with this? Can I have a plus on the chat? Then we can move to the next one. Okay. So I hope all of you are not feeling sleepy because this was a very lengthy. So we will not be implementing anything. I think that's it of our implementation for today. Too much information. Then we will talk about just ideas. Okay. Okay. So brute force can also be used to, let's say, solve some sort of Sudoku. Okay. So if you're given a Sudoku puzzle and you need to find out the number of solutions for that, you can like have a code, and for every paper in the morning, you can just quickly run a code and get solutions for that, right? You can write a self Sudoku code. I've written it once, one when I was practicing back maybe 2-3 years back. So you can write simple Sudoku codes, right? So I hope all of you know what the rules of Sudoku is, that you have bigger squares, and then in each of the row, in each of the column, every number should be only once, and in each of the like 3 by 3 square, there should be every number at most once. So with these, fill the squares with some of the numbers given. So for that as well, you can solve using brute force by placing numbers and trying the next position if it fails or not. Okay. Of course, there are even better algorithms to solve it faster, but we don't want to go into algorithm optimization right now. Okay. There is something called algorithm. So there is something called algorithm X, which uh, improves on all these things. Like it's an advanced version of brute force, but it's very suspicious name. Suppose the question needs to return who could have captured most squares if both played optimally. So both are playing optimally, right? Suppose the question needs to return who could have captured most squares if both played optimally. We can use, right? So if it's positive, then first player captured more squares. If it's negative, then second player captured more square. I'm not really sure. Like the difference of A minus B can be used to find out who got more, right? Like we are finally getting player 1 score minus player 2 score. Okay. Yeah. So we can I would say total number of moves. No, in that case, I think it will be difficult. Number of squares captured. So number of squares captured, you can perform, you can find out. It's just like along with like that score, you will also have to find out the total number of squares captured, and then from that sum and difference, you can find out player 1, player 2. Like when you terminate, when you are there is no move. Along with 0, you return the number of squares, like total number of squares that are currently captured by any of the players. So that's like player 1 plus player 2. So you can return. Yeah. Yeah, you can have global counter. Yeah, exactly. That's a better way. So can we have a global counter in Morty? Yeah, that's a, if the question was find out the exact scores for both of them in that particular scenario, it's better to like have like uh like a boolean which says that whose move it is. Okay, we can call, yeah, that's also possible, counter and mod to, yeah. So yeah, it's generally implemented in that way, like boolean play, is it player 1 move, is player 1 move, something like that, and that's how you okay. So for Sudoku as well, I hope you can do that. Like I'm not going into the details of this. This is very straightforward. So let's talk about one more problem. Let's say we have okay. So now we will talk about a bit of recursion in specific. Okay. So till now we were talking about brute force, but this problem is on recursion individually. It's not brute force directly. Okay. So let's say there is a n cross m, let's say piece. Okay, n cross m paper, or let's say there is an n cross m M chocolate, okay, Cadbury chocolate, and there are like small chocolates of Cadbury in the places. Okay, so it's a Cadbury chocolate. I hope all of you have seen how they are like broken down into blocks. Okay, so there is n cross m such blocks. Okay, and now what we want to do is we have to divide it into k pieces. Okay, we have to divide into k pieces. Like let's say k of the friends are want to have chocolates, and specific requirements are each of the piece should be a square. Okay, so we have to divide into k squares. Make sense? Like each of the piece after breaking out is square. Also, when you break a piece, like this is a piece, if you want to break, you have to break it along like full line. Like you have to just take it and break it along one line of the chocolate. That's how even you can. That's how it generally works. Okay. So when you take a chocolate, you have to break it along one of the lines. Okay. Like either this or maybe this, something like this. Okay. So you have to break it. Once you break, it breaks into two different parts. So one will be something like, let's say if you break it along this line, one would be something like this, and the other one would be like this, and then you cannot like break it together. You have to break each of them individually now. Okay. Something like this. Okay. So it will break off, and then you have to break this and this as well. Okay. So now with this in place, like this is something defined. Now we will define some metrics and we will try to do this. So we can break it in k pieces in a lot of different ways, right? So we will define something called cost. Okay. So when you break along a line, okay, something like this. So its length square is cost. Okay. So over here you have like 4 pieces joined, right? And you are breaking it. So you will have to incur a 4 square cost. Make sense? So if you have something like, let's say 2 cross 3, if you break it along this line, this line over here, so it will cost you 4 square. If you break it along this line, it will cost you 2 square. Okay, something like that. I hope you got the point, right? This is the cost of breaking it. So you have to break the whole chocolate into k pieces, each being square, such that the total cost of breaking is as minimum as possible. Okay. And we don't really have constraints right now. You can think of any brute force solution. Okay, just like any way, any idea to just solve it. How do we just maintain it? How do we solve it? That's the main thing. Okay. We are not talking about constraints and will it pass or not. How do we even do this? Okay. So given a chocolate n cross m, you have to break it. For every break, it will get split into 2 different parts, and they will now act like individual parts. For breaking along some line of length L, it will give you a cost of L square. Okay. Now given k pieces and given this particular large piece of n cross m, you need to create k pieces, each being a square. Okay, so by square I mean to say it should be of a cross a dimension, where a can be anything from 0 to from 1 to n, min of n comma m. Okay, so any of these dimensions, find out what is the minimum cost that you have to pay. K into area of square. Okay, so area A is not fixed. Each of the squares can be of different dimensions. So let me give you an example. So you can have something like this as well. So let's say this is the thing, and you have, let's say you have to break it into 5 squares. So what you can do is you can have one square something like this big square, and then 4 smaller squares. Okay. So you can do it something like this as well. Okay. Yeah, the total, of course, you don't want to waste things. So it's not necessary. Like you can throw chocolates if you want to. So the main thing is each of the piece should be square. So you can throw off pieces if you want to. So like k into area of square should be less than equal to m. Okay. So you if you want, like you can throw off pieces. That's perfectly fine. Is the question clear to everyone? So there are a lot of things in the question, but the gist is chocolate break in such that cost is minimum. Cost for breaking along line of length L is L square. You need to break it into k pieces of each being a square. You can throw off pieces if you want to. Find out the minimum cost. Okay. So how do we think about it? Like how do we even like think about this problem? So even some brute force or any code. How do we solve any brute way? Any ideas? So think about this for maybe 1 or 2 minutes, and then we will discuss. Okay. if you have any question, you can ask, but like clarification. But this is the whole setting. You need to find the cost. So what would be? So we'll generally try to use some sort of recursion. That's a hint. So how do you design the recursion? That's it. True. We need to decide an order of the cut. True. Yeah. So one more thing, like this is important. That let's say you are this 4,4 piece, right? So let's say you have this 4,4 piece. So once you cut along this line, they will become two independent pieces. Okay. And then if you cut along this line, it will. If you cut along this line, it will just cut this piece. It will not cut this piece. Okay. So you will have to make separate cut to this piece. Yep. So for every piece, you have like some finite number of options, right? Like either a row cut or a column cut. So we can of course try on all of them, but how do we maintain that k square property? Okay. So I think, yeah, okay. So I think what Vijay is suggesting is something like this, that, okay, we have a n cross m piece, okay, and what we will do is we'll cut it somewhere, and then we will keep like a set of rectangles that we have, okay, and we have some n cross m, we will cut it somewhere, and we will add this n comma x and m minus x comma n in two pieces, and then again pick one of the piece, cut it, and so keep cutting so that we get it right. Benil, I'm not sure what you are like suggesting. A into B rectangle, minimum A minus B square plus min of AB. No, there is no like fixed answer for this. So how is this ensuring that you have K number of squares?
No, every single square is like one cross one. So since we have a rectangle, we
So
take
no, so square should not be like so.
no, because you can throw away chocolate,
Yeah,
right? So that's
yeah. Okay, so you're saying that we will make squares of 1 cross 1 only. So even 2 cross 2 is a square, right?
yeah, but
Like you're suggesting that okay, 1 cross 1 will always be optimal.
yeah, I just think I'm not really sure.
Okay, so in case of like let's say we want two squares from 8 cross 2, so sorry 4 cross 2, so that's just one cut, right? Why would we make 1 cross 1 in that case?
What is the question? 2 cross 4.
Yeah, so it's like 2 cross 4, and we want two squares out of it, so we just cut it over here and we get 2 1 cross 1. So why would we go to 1 cross 1 in that case? If we are allowed to
Yeah,
throw, then we can eventually get all pieces down to k 1 cross 1. Yeah, so it's not always 1 cross 1. Like we don't want to get into all cross 1. So this is something that we'd be looking at even now today, and in like when we start doing some sort of DP and building the recursive thinking. This session was more on brute force and not on recursive thinking, but this is the hint that how do you think what to keep so that you can like enumerate the solutions efficiently, right? This is something called like building the states or something like that. So what do you keep so that you can enumerate on this, right? So let me give you some idea. So of course there is some brute way in which what Vijay was suggesting, that after each move we have k squares. So what he was suggesting something like the keeping piecewise definition, like what are the pieces that are available right now, right? We don't want number of moves, that's anyways irrelevant. Like yeah, number of moves can track that number of pieces, but anyways we don't need number of moves for us. Like yeah, you can like, you will anyways have to save all these pieces, right? So you can just enumerate on them. So number of pieces doesn't make sense. After each move, you can check if, so after each move, yeah, if we have case watch, that's one solution. That's a very brute way, but that's a good solution that we can like keep on cutting, and we will see that after every cut possible, can we make a solution. But that's a very big, like a very big complexity problem, because every time you are having multiple choices, and in each of the choice you have multiple positions to cut and a lot more thing, right? Makes sense. So like there are too many choices to handle over there, right? But it's a solution. Okay, so like you keep on dividing pieces, and each piece you like group on rows on columns, and based on that you decide. So let's try to think about what we can keep in recursion. So just a simple recursion can solve this particular problem. Let's look into that. So let's say we keep a recursion of, let's say my like one dimension is n and another dimension is m, and we need k number of squares from this. Okay, so now there is a n. So what this suggests is there is a n cross m rectangle, right? Now what we'll do is we will try to cut it on all like on all rows, on all columns. Okay, so what can be the split? Either it can be 1 comma n minus 1, 2 comma n minus 2, and so on up to like, let's say n minus 1 comma n. That's the only n minus 1 comma 1. These are the only possible splits, right? Here, cut here, and so on. Cut here, cut here, cut here, and so on, right? These are the only possible groups. Also, we can also have something like 1 comma m minus 1, 2 comma m minus 2, and so on up to m minus 1 comma 1. These are the only possible cuts, right? If like we cannot of course make any of them 0, like all of them are positive, that's to be guaranteed. Okay, now there is this k, right? So now from this n comma m we need k pieces, k pieces of square. So we can also decide on, so after one cut it will get into two pieces, right? Some n comma, let's say we are cutting on columns, so it will be x and it will be m minus x comma n, right? This is the piece. So out of these k squares, we can delegate the task to find out k squares to, let's say, some y number of squares from this and k minus y number of squares from this. Okay, now can you see that this is the exact same instance of the exact same smaller instance of the same problem? Find out the minimum. So we will find out the min cost. Okay, find out the minimum cost to make y squares out of this n cross x dimension, and find out the min cost of making k minus y squares out of this m minus x comma n. Okay, so of course we don't know this y, so we'll iterate on all possible ways, either 0 or k, either 1 or, let's move this a bit down, 1 or k minus 1, so on up to k or 0, right? These are the only possible choice, right? But recursion is all about dividing the same, like deciding what to keep so that you get into the same instance of the same problem, like a similar instance in the smaller problems, right? So if we keep the k, like how many pieces of square do we need to create? The same problem is getting divided out of, like there are only these choices, like either you do, there is a choice with a cross product with all these choices, like you have to make a split. Again, we have to make a split of k's, but that's okay. We don't want to think about complexity right now. Okay, you can enumerate on all possible choices of these, like where to cut and how many squares to give to what part, and based on that you get a smaller instance of the same problem. So it will be nothing but whatever this particular recursion returns plus whatever this returns plus the cost of this cut, that will be nothing but n square, right? Make sense? Is this clear to everyone what we are doing over here? Or else like just ask me which part is not. So what we're doing is we are defining this recursion in such a way that, let's say I have a, so whenever thinking about recursion, it's generally better to think in terms of like in words, like what we are keeping, what is the states and what is the, like in recursion this is called states. Okay, even in DP we will use this term, something called states in dynamic programming, but even in recursion this is called recursion state. What is the parameters that we're keeping, what is the state of the parameters? Okay, so this is called states. Okay, and what are we returning? So we will design a recursion which says, given a n cross m rectangle, n cross m chocolate piece, what is the minimum cost to make k squares? Okay, make sense? So when we have this instance, we have to break it into smaller pieces. So we have to make a move. What is the move? Make a cut, right? So based on that cut, we have to divide on which side. We will divide into two smaller problems, and it would have been difficult to keep track of this k, right? That how many squares one of them is producing. So that's why we introduced this k into the parameter of the recursion itself, so that we can decide on, okay, let's say we want to create y and we want to create k minus y out of this. So that will get like that the recursion will handle that. Okay, my recursion over here will give me at least y pieces, or it will return me, let's say, very high cost. Okay, very high cost, so that it's not possible, something like that. Okay, and we can keep something like that in track. Make sense? Is this idea clear to everyone? Then I have a plus one if this is clear, like what we are doing. So this is just designing the same recursion efficiently. You can of course design it in a lot of different ways, and you can solve it in many different ways if you want to. But like if you think about this, like let me just show this, just how simple it becomes when you in fact code this particular problem. So we are given, let's say, nmk, right? So we are given nmk, that are the number of the sides of the original rectangle and the number of required rectangles, required squares. So we just now need to print the recursion of n comma n comma k. So we are using the inputs as the recursion parastate. So make sure, always think if the inputs itself can be used as a parameters of recursion in some problem or not. Most of the cases that's the case, but in sometimes you need to add something based on that problem. That will those things we will learn in DP. But anyways, in most of the cases, it's direct trivial to like understand. Okay, it's just working. So in this problem, the numbers can go a bit large, so we will have long. Okay, so I'm just keeping things in long. So let's say rec of, so so we need this many squares, let's say. Okay, let's say if needed equal to 0. So if we don't need any squares from this, can we say that we just return a 0 cost? Because why to break it if we don't need any squares out of it, right? Why will we even break it if we don't need any squares? Make sense? If let's say if I into j is so there is a small pruning, anyways, not needed, but still, if I into j is needed, is less than needed number of squares, can we safely return something like 1e15? Because it's like something like infinity. You can return 1e18 if you want to, but something like it's not possible. That's what I'm saying. Make sense? Like even if you divide it into all 1 cross 1 pieces, it's not feasible. Like, it's not possible to create needed number of squares. Okay. And if I into j is equal to needed, okay, so what we can say is we have to, let's say, if okay, so this is something similar, like if I is equal to j, and we have to, let's say, find out square. Okay, sorry, 0. Sorry, yeah, that's a 0. Yeah, and or else the answer would be let's say we keep it as some infinity, and then we like brute force on all possible splits in, let's say, the horizontal part. So let's say from 1 to I minus 1. Okay, so this is like a quick brute. So we will also brute on how many k's, like where all the neededs will get splitted. So int k equal to, let's say, need 0 to k is less than equal to needed k plus plus, and then we will just take answer equal to min of answer comma recursion into I into row number of things, column remains the same, k number of things plus rec of I minus r j k needed minus k, plus the cost would be, we are splitting across row, so the cost would be the length of column, so that would be j into j, right? That's all for this part, and we need to do the same thing for column as well. So I'm just quickly using the r variable itself just to not write much of code. Okay, and this would be I into I, right? So these are column breaks. Okay, and then just return answer. So that's the all possible ways in which you can break it up, right? Okay. So this is how you can like break it off, and this is like the quick recursive solution for this particular problem, right? Is this code clear to everyone? Is it clear to everyone till now? Can I have a plus one in the chat from everyone? If like, I think some of you might be sleepy by now, but anyways, so we have been implementing a lot today, but I think that's necessary. Now I think that's the whole solution in recursive form. Just a quick sneak peek onto what we can do with these things. So what happens is in this particular problem, these parameters would be reused. So let's say so we'd be talking about, let's say, if you have some square and you need k number of pieces, and then you break it like this, and then you reach to like this and this, and then you reach to smaller square with some x number of needs, and then you have some other splits done first, and then you reach the same particular sub solution with x number of needs. So this type of sub solutions will be required a lot of number of times. So that's the whole idea of dynamic programming. If you think about it, we can just simply keep like a DP array to, let's say, some different values that are needed. Okay, and just like write few lines that if, so what we will do is we will initialize DP array with, I'm just giving a quick sneak peek. So we can use DP to solve, just optimize this particular code a bit more. Why? Because then set DP comma -1 comma size of DP. So just storing the recursive values, because this states can be repeated a lot, is called DP. Okay, there is no fancy thing in DP, dynamic programming. If is equal to -1, then we calculate. If is not equal to -1, sorry, then we let's say return the answer. Like if it's already calculated, the answer will always be positive. So we just have it and saved in an array, or else whenever we calculate, we also store it in the variable needed. Okay, makes sense. So this is all. So earlier it was all brute force, like you had a brute force way to solve this. Now the time complexity will run like, so that with just this 3 lines of change, 4 lines to be precise, the time complexity goes from exponential to n into m into k multiplied by n into m into k. This is now the whole complexity for this problem. Now we will look into why this complexity dropped suddenly, because we are not recomputing anything again. That's the way. But we will look into how these things are coming out. But this is the whole idea of DP. If this is like a quick go to what DP means, if you ever hear it somewhere, this is just like you have a recursion in which same states are getting called again and again, and the answer is also same. Just save that value in some array, global array, and just return it if you have already calculated. That's DP, and that just brings down the exponential complexities of recursive functions to the number of states there are. Like there are 10 to power like n into m into k number of states possible, and for each state you have n plus m number of n plus m into k number of computation. So that's so this would be n plus m. Okay, so this is just a quick go to what DP is. But anyways, while doing DP, the main thing would be to think about this recursion, right? What are you keeping in recursion that would help you to solve the problem further, right? And that's the whole idea. Okay, so you can forget about these parts, but the main thing is how do you decide on what to keep, so that the smaller problem is a instance of the bigger problem. And if you are designing the, like, you don't need to think about how is it calculating too much. If you are like keeping the parameters right and you're designing the recursion transitions correctly, recursion works in this way that, okay, I have this function, it does the work correctly. So if I know that it works for my smaller sub problems, and if I can combine those solutions, it will work great with the bigger one as well, right? So if these are correct, if these mergings are possible, and if the optimal values of smaller ones are used, so in that way it can be reused over here, right? So that's how we design these states. And like we keep in states whatever are needed. So this keeping this number of rectangles, squares needed really helped us, right? So we can also think about in this terms, like let's just change the problem a bit. Let's say you don't want like k squares, you want to give you want to cut let's say cut the chocolate in such a way that you get at least one piece with you get one rectangle with length with a you can give someone k pieces of rectangle, like k small pieces of like k total pieces of rectangles. Okay, so there are n into m number of rectangles, smaller squares in the total rectangle, right? In n cross m, you have k, you have to give someone k number of pieces. So how do you split so that you can give him exactly k number of small pieces, even in this shape? Let's say you can think in this problem. Let's say you have something like a 4 comma 2, sorry, 2 comma 4, and you need to give someone 5 pieces. So what you can do is you can cut it over here and then cut it over here. So you can give this 3 piece from over here and this 2 piece, so to make him to give him 5 pieces, right? So let's say this is the problem. So in that case, you can, the same state will work in that also. You just need to change this, that okay, if I into j is equal to needed, then just returns it. That's it. That's the only change. Okay. So you just need to think about what to keep in things, what to keep in as parameters in recursion, and how to use them internally. So it's like you try to use the recursion, and you feel like, okay, I need to split the number of needed rectangles. So I need a needed rectangle in the state. That's how you like think about how what to keep. So we will of course take up more problems like this when we start like recursion and DP again after one like on the next week. So we will discuss more problems like this with much more simpler ones, but this was just a quick thinking about how do we check if the base case will avoid infinite recursion. um, that's just, I think there is no direct way. Yeah, okay. So if you're always like getting a smaller instance of problem, like you have some instance of problem, like there is a bigger instance, and you are sure that it's always getting to smaller parts, and the smallest it gets to, you are handling that particular thing, then of course it's going to break, like, right? Like that's the whole thing, right? Like what is the smallest piece it can boil down into, and just make the answers for them available. That's how recursion works, right? So I think if you are like thinking about what is the smallest piece your recursion can stop at, so just answer like keep base cases for those cases, and the rest will be handled by division, right? Like, so I think that's all for today's session.